All right, this is the calculus midterm for review guide for 2024. So we're going to start off with the first question. Right away, excellent job here. So what is the derivative of sin over 2x? So we got to take this derivative. So we don't know what si or n are, so they could be functions or they could be constants. So we have to kind of treat them as their own individual functions. So that means, again, when the letters are next to each other, that's s times I times n. So that's going to be a three-term product rule. So that's pretty good. And then it's combined with a division. So we know we've got to divide by 2x. So we're going to have to do both the quotient rule and the product rule for this one. So that's kind of nice. And this person decided to make it pretty tough by doing all three terms together. So let's check out what we got. So quotient rule part, I think everybody's pretty good with. So we'll do low d high. So we'll take the derivative of sin minus high sin d low. So the derivative of that is just 2. So that's pretty nice. Square the bottom and away we go. So 2x quantity squared. All right, so we have to take the derivative of sin. So if we do that, again, this is a product rule. We could do it as a three-term one, or if we want, we could think of it as s times in. If we think about that in terms of s times in, let's just say this is f prime equals. So the 2x is still here. But for this part, we have to take the first, so that's the s, times the derivative of the second. So that would be in. So let's just write that as the derivative of in, because we don't know what that is yet. So this is a big parentheses. So first times the derivative of the second plus the second, so that would be in times the derivative of the first. So that's s prime, or dx if we want to do it that way. Cool. Everything else in blue stays the same. So minus 2 sin, or sorry, 2 sin. That's not 2 sin. Sine would have to obviously have the parentheses in some sort of argument. Over 2x squared. All right, so now we still have to do this part, which is the derivative of in, but this is another product rule. So we've got 2x, and then we've got the big parentheses in purple. So that's s times, and now we have to do the derivative of in. So that would be first I times the derivative of the second n, plus the second n times the derivative of the first I. All right, so that's that part. And then plus, we still have I n s prime. Okay, and then minus 2 sin. All right, over 2x squared. All right, so we finally did all the derivatives. So again, pretty big one because we had to do both quotient rule and some complicated product rule stuff. So now I think we're ready to pick the answer because only one of them has these excellent derivatives in it, and that's going to be B is going to be the answer for that one. So there we go. So nice job here making that look like sine, but it's not sine because again, sine would have to have like a sine of x or a sine of 2x. So that's a good one to try and trick people and try and think that that's supposed to be sine. So very nice. Cool. All right. So nice little quotient rule one, product rule one. Pretty tricky, but hey, good to have some tricky ones on the test. 2. Palmer eats 4x squared chocolate calcs per minute. What's the correct unit of the second derivative? B. So we know that right now. So the function is currently in chocolate calcs per minute. So if we take the derivative, that's going to be chocolate calcs. We have to add one more unit on the bottom. So that's per minute squared. And so the second derivative, we add another one on the bottom, so that's chocolate calcs per minute to the third power. So that's going to be E down here. So pretty nice. So again, good job with this one. Again, starting off kind of hard because it's already starting off as a rate. So you're taking 2 more derivatives. So again, that's one that people are going to get caught out on and maybe pick A by accident. But good question. So very nice. Next, we got a little dreads question. So it says a spherical balloon is being filled up. So we got a nice balloon. So we can draw a nice balloon. All right, it's being filled up and its volume is increasing at a rate of 10 cubic centimeters per second. Instead of cc, we'll do cm cubed per second. All right, at the moment when the radius is 4, how fast is the rate changing? All right. So they don't really say what the rate of what changing. So we're going to have to assume it's going to be the rate of the radius, because that is, according to the rules of English, the previous thing. So that's what it has to be describing. So we have to go ahead and make our rate box then. So for our rate box, let's see what we got. We've got 10, so dv dt is 10 centimeters cubed per second. All right, we want to find dr dt, so that's our question mark. We know r, radius is 4, so that's good. So that's our rate box. This person decided to not give the equation. Some people did. This person did not, and that's fine. It's an easy equation, 4/3 pi r cubed for the volume of the sphere. And the reason that's a good one is because when we take the derivative, again, this 3 from the power rule is going to cancel out this 3. If we wanted to write it out, I'll write it out since we're doing a review. 3r squared dr dt. But again, when we substitute and solve, we can see that these 3's are just going to cancel out. Ooh, this is not v, this is dv dt. So we know we got 10 is equal to 4 pi. The radius was 4, so 4 squared dr dt. Again, we're trying to figure out dr dt, which means we got to move all of this stuff to the other side. So divide both sides by 4 pi 4 squared. So if we do that, that's going to be 10 over, let's reduce. 10's even, so it'll be 5 over, so 16 times 4 is 32, or sorry, 16 times 2 at this point. Just go ahead and make that. 16 times 2 is 32, so we got 5 divided by 32 pi is equal to dr dt. All right, so this is not in terms of pi, which means we actually have to do the math here. That's all right, that's fine. 5 divided by 32 pi is not too crazy. Just because we know pi is about 3, and it's a little more than 3, and this is a little less than 33. So 32 pi has to be about 100, and so 5 over 100 means that 5 over 32 pi, it's kind of like doing a little percentage. So 5 over 100 is about 5%, or about 0.05. So none of those are the answer. I'm guessing that this is just a little typo. That decimal point should probably be there to get to 0.05. Again, for AP, you want to do 3 decimals instead of 2 decimals. But that would be my best guess at this one. That's kind of where we're at. Again, even though we got a lot of different answers, again, this process of doing the dreads is more important because, again, the questions are going to change, but being able to do the process is going to be the important thing. All right, next up we got 4. Devin only goes to school if there's math class that day. This function is described as d of m. So we have d of m, with d being Devin and m being math class that day. What would be the units on the first derivative? All right, so we have to kind of think of this in terms of something else that we know. So this is going to be a pretty tricky question. So we know that if we have a function like s of t, so that's one we're familiar with because that's just our position function. We know that this is measured in seconds, and this is usually measured in meters, or feet, or some sort of length. So when we take the derivative, if we were to do s prime of t, we know our units are usually going to be in like meters per second because that's a speed, or again, feet per second, feet per year, whatever you want those to be. So if we kind of analyze this over here, we're going to have to kind of match up our units. So our D is, again, like our meters. So that's going to have to go on the top. So we're going to have Devin on the top. And then our M is kind of like our time here. So that's got to go on the bottom. So Devin per math class. And that's going to be choice C here. All right, so there we go. So I like that one. Very nice. That's really going to stretch your brain because, again, you have to relate that back to something you know. So it's kind of tough. But nice job with that one. So pretty good. All right, next up, find the third derivative when f of x is 3x cubed plus 2x squared plus e to the x. So that looks pretty straightforward. So we're just going to kind of do some derivatives. So the first derivative, we'll use the power rule to get 9x squared plus 4x plus, and the derivative of e to the x is e to the x. We'll get the second derivative in. We'll do power rule again. So 9 times 2 is 18x plus 4, and then the e to the x stays the same. And we got to do a third derivative, because that's what this question is asking for. So power rule again would give us 18. Remember, derivative of a 4 would be 0. And then we've got e to the x is still just e to the x. So that's going to give us e 18 plus e to the x. Nice. All right, 6. At the zoo, lions are watched by passing viewers. What units could be used to represent the rate of lions viewed per person's second derivative? So again, this time we're starting at the rate of lions viewed per person. So that would be lions per person. And then we need to get the second derivative from there. So again, this is f. So if I take the derivative, that's going to be f prime. Again, I'm going to assume, because this one was kind of tough to figure out exactly, but I'm going to assume that we're going to take the derivative with respect to people based on the answer choices. So lions per person squared, and then the second derivative would be lions per person to the third power. So that's going to be d. I think that's what we want to do. Again, not really saying what we're taking the derivative with respect to. Again, I assume this was with respect to people, but if it was a little different, if it was with respect to time, we'd get a different answer. So again, we have this hour over here. It's like, okay, so if we did this with respect to time, again, this is going to be the same first derivative, same function, but the first derivative then is going to be lions per person per hour, because again, if we're doing it with respect to time, we have to put a time unit down here. And then our second derivative would then be lions per person per hour squared. So again, just watch out, just make sure you're seeing what we're taking the derivative with respect to. Again, since it didn't really talk about time at all, again, going back to English class, second derivative would then have to go to the person because that's what's right before it. So again, that's why I'm making that decision. I'm using the rules of English and the way modifiers work. So that's what we got for 6, I think. For 7, given the graph to the right, find the limit as x approaches 0. So we can see that these are going up to infinity. So we're going to pick infinity. So that's a good question. Nice little reminder with the graphs. Again, on a question like this, like one of the answer choices would never say DNE and infinity. It would be one of the two. In this case, this one person chose infinity instead of DNE. Just be aware DNE would also be a correct answer. All right, number 8, find the derivative of this function. That looks like a pretty solid quotient rule. So we're going to do low d high. So the derivative of this is 2x minus high, x squared plus 1. D low, that would be 1. Square the bottom, and away we go. All right, so that's what we got. And then this person decided to simplify the top, so we got to multiply the whole top out and figure it out from there. Totally fine. We'll distribute this 2x to both parts, so 2x squared minus 4x. Then we have to distribute this minus sign to both parts. Since multiplying by 1 would just keep it the same, so minus x squared minus 1, still over x minus 2 squared. Combine our like terms. 2x squared minus x squared is x squared minus 4x minus 1 over x minus 2 squared. Hey, all right, there we go. X squared minus 4x minus 1. Perfect. All right, there we go. So that's what we got for that one. I think we're good there. Okay, cool. For number 9, we got to get the 1,634th derivative of sine of x. So here we have to just remember it's just a 4 cycle. Since we're dividing by 4, we're just going to use the shortcut and just divide the last one. So 34 divided by 4 is 8 with a remainder of 2. So we're going to do 2 derivatives. So we start with sine. This is like f. So then we have to do first derivative. This would be sine of x, they said. So then first derivative is going to be cosine of x. And then our second derivative is going to be negative sine of x. So that's how I want to pick C. Just as a reminder, if we were to do the third derivative, that would be negative cosine of x. And then if we did the fourth derivative, we'd get back to sine of x. So remember, it kind of goes in that cycle. All right, for 8, we have to evaluate the limit. It's a memorization one. The answer is 1. Done. For number 11, we find the derivative of 2 times 2x, the quantity 2x plus 3 squared. So in here, this looks like this is going to be a chain rule. So you could either use the chain rule or the general power rule would be okay too. I'm just going to go with the full chain rule just to review the chain rule. So we're going to say u is equal to 2x plus 3. And then y is going to be 2u squared. So u prime is going to be 2, because that's the derivative of 2x plus 3. Y prime is going to be 4u. So again, remember, we're going to take that 2 and bring it down. So our overall derivative is going to be 4u times 2, which is going to combine to become 8. And then u was 2x plus 3. This person also multiplied everything out, so we'll go ahead, we'll distribute. So we get 16x plus 24, and we get e. So there we go. So that's going to be our derivative. Cool. All right. For 12, we got to find dy dx given our equation with some y's and x's. So this is an implicits question, so we'll just jump right into taking some derivatives. So the derivative of y to the third is 3y squared dy dx. Then the derivative of y squared is 2y dy dx. And then the derivative of minus 5y is minus 5 dy dx. And then the derivative of minus x squared is minus 2x. And then the derivative of negative 4 is 0, because negative 4 is just a number. So I'm going to be pretty quick to move this over to the other side. There's only one thing to move. So we have 3y dy dx plus 2y dy dx minus 5 dy dx equals 2x. So we have all the dy dx's on one side, and our next step is we have to GCF out the dy dx. So we get 3y plus 2y minus 5 inside the parentheses. And then our last step is we're going to divide by what's in the parentheses. So we get 3y plus 2y minus 5. All right, so let's see. That looks like that's going to be, looks like it's this one. No, that's having a negative. This one? Yeah, there we go. Positive 2x. So 2x over 3y squared plus 2y minus 5. So there we go. So pretty good for 12. That's implicits. So very straightforward, just kind of runs through that 4-step process. Next one, for this piecewise function, find the limit as x approaches 4 of x squared minus 2x minus 15 over x minus 5 when x is greater than or equal to 4, and x plus 3 when x is greater than or equal to 4. Cool. Very nice. I like that one. That's a good trick question. So it looks a lot like some of them that we did where you just kind of plug them in and make sure they're the same. But this is a one-sided limit because we don't know what's happening before 4. So we can't actually find the limit as x approaches 4. Yeah, that just doesn't work because this would be one-sided. The limit as x approaches 4 from the left of our function does not exist. We could find the limit as x approaches 4 from the right. Like we could find that one, the limit as x approaches 4 plus. Maybe we could do that. It would have to be the same because these are two different equations. So hopefully they're the same. If not, then it doesn't exist on this side either. But we could check it out. We could try it out. If we plug 4 in, we get 4 squared minus 2 times 4 minus 15 over 4 minus 5. So let's see, 4 squared is 16, minus 15 is 1. 1 minus 8 is negative 7 over negative 1 equals 7. On the bottom, we have 4 plus 3. which also equals 7. So, I mean, I guess we could kind of say the limit as x approaches 4 from the right is equal to 7, because it does work for both equations. This isn't really a function, so it's not really a good choice, but I mean, I guess that's true. But overall, again, since this doesn't exist on the left side, overall doesn't exist. So I really like this one. This is another good one where it looks like it's going to be super easy and straightforward, but it just kind of catches you out because if you don't read the question, if you don't actually pay attention, you miss it. You miss the whole concept here of the limit has to exist on both sides. So I like that one. I like that's a good way to test that the limit has to exist on both sides. So good one. I like that one. Next up, we got to find the limit as x approaches 2. Seems pretty easy. We just plug 2 in. So let's plug 2 in and see what we get. So 2 to the third minus 3, 2 squared minus 12 times 2 plus 20 all over 2 to the third minus 2 squared minus 8 times 2 plus 12. All right, so if we do that, let's see what we get. That's going to be 8, 16 minus 4 times 3 is 12 minus 24 plus 20. So that's 4 minus 4. Uh-oh. That's going to give us 0. So now I know I'm in trouble. So I'm just going to start erasing this equal sign. No, you know what? I'm not. I'm going to live dangerously. I'm just going to make 2 equal signs. So on the bottom then, we've got 8 minus 4 minus 16 plus 12. So we got 4 minus 4 again. Yep. So that also equals 0. So since I've got 0 over 0, this is indeterminate form. So this is a L'Hopital question. So that's good. All right, so we got a L'Hopital question. So we're going to L'Hopital it. So let's L'Hopital it. So that means we need to find the limit as x approaches 2 of the 2 derivatives. I'm going to do the derivative of each of these. So if I take the derivative of this one, we're going to get 6x squared minus 6x minus 12 over 3x squared minus 2x minus 8. All right, sounds good. Seems pretty reasonable. Let's go ahead and we're going to plug 2 in. Again, just in case this is not going to work out again, let's go ahead and do the 2 equal signs again. The top, I'm actually going to factor out that 6 because I don't really like that 6. I think it's going to be easier if we take that out. Minus 2 over, so we get 3 times 2 squared minus 2 times 2 minus 8. So this is going to be 6 times 0. On the bottom, we're going to get, because this is 4 times 4 minus 2 minus 2. Here, this is going to be 12 minus 4 minus 8, which is also 0. So again, we get indeterminate form. So we're going to L'Hopital it again. So it's a double L'Hopital. That's cool. All right, like a double L'Hopital is good. So we're going to take the limit as x approaches 2 of this function. So we're going to do 12x minus 6 over 6x minus 2. All right. Again, I feel a little bit more comfortable just plugging 2 in at this point. So 12 times 2 minus 6. And I've got 6 times 2 minus 2. I don't need a parentheses on that 2. All right. So this is going to give us 24 minus 6 is 18. 12 minus 2 is 10. All right, so now I see that I'm not going to get 0 over 0. Thought for a moment we were going to triple L'Hopital it and just get the end. So that's good. Okay, cool. So we can't just kind of cheat on this one and use one of our other techniques. All right, so then 18 divided by 10 is not an answer, but if we divide both of those by 2, 9/5 is an answer. So there we go. So a nice double L'Hopital. Cool. I like that one because it's a multiple L'Hopital, but it doesn't drill it all the way down to the end. So very good question on that one too. Lots of good ones for this section. Which method cannot be used to find the limit as x approaches 1 of x squared minus 1 over x minus 1. Plugging in the value directly. Well, let's try it. 1 squared minus 1 over 1 minus 1. So that's 0. That's 0. Yeah, you can't do that because we would be stuck with indeterminate form. Now, if we have indeterminate form, we are allowed to L'Hopital. So most people would probably L'Hopital that one. So that's good. So we're allowed to do that. But what about the other ones? Factoring the numerator. Well, yeah, we could actually factor that because that would be x minus 1 times x plus 1 over x minus 1. And we can just use factor cancel. So that's actually good. So we can use a different limit technique. Expanding the numerator. So let's see what we do if we do that. That would be x squared over x squared minus 1 minus 1 over x minus 1. And now if we plug in, this is the limit as x approaches 1. If we plug in, yeah, this is actually going to give us some values, right? If we plug 1 in, this is going to be 1 over 0. And on this one, we're going to get 1 over 0. So yeah, and we can see that. So we get somewhere. We don't get a final answer. This is still unknown. So this is still indeterminate form. Oops. Because we get two infinities. So this means we can't really go from here. We don't get the answer directly, but we actually can then go ahead and do some extra stuff at this point. So expanding the numerator would actually work out. So we could actually do that. We can see that, again, if we're going to do that, we're going to end up with the 1 and 1 again. And then estimating using a graph. Yeah, a graph will always work. So that's good. So we could always choose to graph it if we want to graph it. Pretty cool. All right. Sounds good. So just remember, that's what we got. All right. So nice question on that one. For 16, we got arc cosine, find q prime of x. So we're doing arc cosine. So we know that arc sine of x is going to be, we're doing x, right? So that's going to be 1 over, because it's x and not u. So remember, u would be u prime on top. But we got 1 over 1 minus x squared. So that means if I want to do arc cosine of x, that would be negative 1 over square root 1 minus x squared. Okay, so that's going to be a. So there we go. Pretty good. Another memorization one. So kind of like we had that other limit that was a memorization limit. This is a good memorization for a derivative. Inverse of f and g be the functions that are differentiable everywhere. G is the inverse of f. We got to find g prime of 8. So again, not too bad. Oops, wrong letter. So g inverse prime of 8 is going to be equal to 1 over f prime of g of 8. So we got to find g of 8, because that's the first thing we have to do. And again, we know that g is the inverse of f. So that means that we can go back and forth. So I want to find out where the answer is 8, and it leads me back to 3. So what we got to do is say that the g inverse derivative at 8 is equal to 1 over f prime at 3. And then if I look at f prime at 3, that's 10. So that's 1 over 10. So good use of the inverse rule. So that's what we got for that one. All right, for 18, we got to find the horizontal asymptote. So again, to find the horizontal asymptote, we want to take the limit as x approaches infinity or negative infinity. I can see because we're squaring it, they're both going to give us the same one. So I don't need to double check negative infinity, but just remember it would be plus or minus infinity of 3x squared plus 2 over x squared minus 1. And when we're solving our limits at infinity, we've got a lot of techniques that we could use. If we're doing our technique from unit 1, we're just dividing by the highest power of x. So 2 over x squared over x squared minus 1 over x squared. And then each of our limits, we get 3 plus 0 over 1 minus 0, which gives us 3. All right, so, and again, we know that it's got to be a y, can't be an x. X is our vertical asymptotes. So there we go. So again, you got a couple techniques. Again, if you wanted to L'Hopital that one, you could. That would probably work out. Again, if it's free response, before you L'Hopital it, you do need to write out the limit to show that you're doing that limit. All right, 19. Find the derivative of f of x equals negative sine of 4. All right, another good trick question. Sine of 4 is just a number. So derivative of a constant is 0. All right, pretty good. Nice. All right, estimate x equals square root of 15.5 to the nearest hundredth through differentiation. So I had to change this because, again, AP is not hundredths, AP is thousandths. You're not going to get 2 decimals, you're always going to get 3 decimals. So I had to add a couple decimals onto this person's 1 just to make it AP ready. I forgot to change the question, but that's okay. So we got to figure this out. Now, this is really tough because this person made it an x equals equation instead of a y equals equation. So we can't really rely on our good friend y minus y1 equals mx minus x1 because, again, x is taking the place of y in this case, so that's going to get very confusing. So like we kind of wanted to do in second block, we're probably going to have to use the function notation version of this. So f of a minus f of b is equal to f prime at b times a minus b. So we're going to probably need that. Our function, so f, is going to be the square root. So we see that the square root is a function. I can't put an x here because, again, this is x equals. So I have to come up with something else. I don't really know what would be a good thing to pick. So I don't know. Let's pick S because we do S of t sometimes. Maybe that makes sense as like a thing. It looks too much like a 5. Let's make this v for like a velocity type thing. All right, so we have some function here. So then we need to figure out what a and b should be. So 15.5, we have to think about what 15.5 is close to. So 15.5 is pretty close to 16. We know the square root of 16. So that means 16 is going to be the b value because that's the one that we know. 15.5 is going to be the a value because that's one we don't know. So we're going to have f of 15.5 minus f of b, so that would be the square root of 16. I could do square root of 15.5. That probably makes more sense. I'll write that. And then we've got on the other side, we're doing an approximation. F prime of b. I don't really know that one yet. So we'll just kind of put it as a placeholder. F prime at 16. And then a minus b. So that's 15.5 minus 16. All right, so we're all set up. We got to do f prime. So that means we need a derivative. So if we take the derivative of square root of v with respect to v, so that's going to be f is equal to v to the 1/2 power. So this is a nice power rule. So it's good that somebody did a square root power rule just to review that. So f prime is going to be 1/2 v to the 1/2 minus 1. F prime is 1/2 v to the negative 1/2. So f prime is 1 over 2 v to the 1/2, but probably better to write it as 2 radical v. All right, now we know we're trying to figure it out at 16. So we can plug 16 in there, and that's going to give us our value for f prime at 16. So let's clean this up and see where we're at right now. So radical 15.5 minus 4 is about 1 over 2 radical 16, okay, times negative 0.5. All right. I think I'm going to add this 4 to the other side because this is what we're trying to figure out. So radical 15.5 is about, all right, let's see what we got here. So this is 1 over 2 times 4. I think this is going to be easier to write as negative a half, and then plus 4. Cool. All right. All right, this is coming together. So radical 15.5 is about, I think I'm going to combine all of these to become negative 1 over 16 plus 4. So that means we need to add 4 and 1/16. So we got to figure out 1/16 as a decimal. Not too bad, because we know 1/2 is 0.5. 1/4 is half of that, so 0.25. 1/8 is half of that, so 0.125, because 125 times 2 is 250. And then 1/16 is going to be 0.0625. All right, so we have to do 4.0000 minus 0.0625. We'll do some fun elementary math. We'll make these all 9s and a 3. Do a little borrowing. 10 minus 5 is 5. 9 minus 2 is 7. 9 minus 6 is 3. 9 minus 0 is 9. 3 minus 0 is 3. AP is 3 decimal points. So the question is, do we treat this like science class or do we treat this like math class? I remember in chemistry, they're probably going to yell at you because remember, we'd want to round that 0.5 even. That rounds down, but I mean, it's math class, so we'll round that up to 3.938. There we go. Very nice. So good use. So nice local linearization. Use it to estimate a function. So very cool. Good question. So that's what we got. All right, and then we're at the final one, which is not going to be as crazy as the last one. We're doing a limit with the table. So we want to find the limit as x approaches -1. Remember, we ignore -1, so we're probably not going to pick that one. I guess we might. It could be like different on both sides. But over here, we're headed towards -2. Over here, we're headed towards -2. Since those are the same, we'll pick B. That's it. There we go. We got them all.